What you're looking at here is called a sandpile. It's a two-dimensional grid where each square contains 0 or more grains of sand indicated by the color. If you have 0 or 1 or 2 or 3 grains of sand, the pile is stable. But as soon as you get 4 grains, the sand topples over, sending 1 grain to each of the 4 neighboring cells. Now if you have a 4 next to the edge of the board, the same thing happens, but one of the grains falls off the edge. Similarly, if you have a 4 over in the corner, then 2 grains fall off. If you have a line of 3s, and you put a 4 next to it, then when that 4 topples, it adds a grain to the 3, giving you a new 4, and then when that one topples, you get a chain reaction. And if you clear all this out and start with a bigger number, say 256, then it will just keep pumping out 4 grains of sand at each step. So after 4 ticks here, we have 4 piles of 4, plus 240 grains left in the center, and all 5 of these are about to topple. And the center just keeps pumping out more and more and more. Now at this point we have 4 cells with 1 grain each in them, but each one has 3 neighbors that are about to topple, so each of these ones will turn into a 4. Also, each time these 4 around the center topple, the center is sending out 4, but each one of those is sending 1 back. So for that particular step in the process, the number in the center doesn't change. Anyway, it goes on like that. But before long, the whole thing always winds down and comes to a stop. If we did the same thing with 512 grains of sand in the middle, we'd get the picture that was on the screen at the start. So as you can see, with just this one simple rule, you start generating really intricate patterns rather quickly. And depending on how you start, you might get a nice pretty picture like this one, or if you just start pouring sand and fast forward, you might get a complete mess. Hey, my name is Michael and this is my video about sandpiles. Now that you know the basics, we're going to take a look at how to implement the rules for sandpiles on a computer. We're also going to look at the original sandpile paper to see why these things were first invented. And finally, we're going to take a look at the mathematics behind sandpiles using this little calculator program, which it turns out also doubles as kind of an interesting puzzle game. So I hope you stick around to the end, because I think we're going to have a lot of fun. Let's get started. Okay, so we're going to make several sandpile programs today, and they're all extensions of GridPad, the sprite editor I made in my last video. Most of my videos focus on this rather unusual programming language called J, and I tend to explain every single line as I go along. But I thought with all the pretty graphics, this video might be interesting to people who don't necessarily care about J. So I'm only going to explain the lines that are specifically about sandpiles, and I'll move everything else to a separate code review episode for people who actually want to learn how it works. So in that video, I'll explain how you can inherit behavior between applications in J, how I'm mapping the sandpile numbers back and forth to colors, how to draw the fancy palette on the side, and I'll also go into a lot more detail on all the other code you'll see on your screen in the rest of this video. And now we get to the fun stuff. This is the keyboard handler, and I'm going to use it to define some shortcuts to help us visualize the steps in the sandpile simulation. So let's say we have some arbitrary sandpile, and we need to decide what's going to happen next in the simulation. The rule is that any cell with 3 grains or fewer is stable, so we only care about values greater than 3. So in this image, all we want are the eyes and the mouth and these little antennae on top, as well as this border. So to isolate those, we can just compare the entire image to the number 3. The basic comparison operators in J work on individual items, so we wind up with a rank 2 array of 0s and 1s. So now this image represents 1 grain of sand for each cell that's going to topple, and we just need to shift it over 1 slot in each of the 4 directions. And that's what these other 4 lines do. Now, a rank 2 array is basically a list of rows. So to shift the image up, we add a row of 0s at the bottom, and then chop off the first row. To shift it down, we add a row of 0s to the top and chop off the bottom. Then left and right work the same way, but they operate at the row level, or rank 1. We lost some sand along the way here because it fell off the edge, and that means we need to make a fresh copy before we nudge in each direction so we don't lose it. But then, all we have to do is take our 4 shifted copies and add them to the original image, and then subtract to remove the 4 grains from the center. So here's what that looks like. It's exactly what we just said, where Y is the original image, GT is the fresh copy we start with each time, shift it up, down, left, and right. Then in the center we multiply by -4, and the result is all of this added back to the original image. Then the update method is GridPad's hook for us to perform our animation. So once I run this, I can draw with sand and it topples in real time. Okay, so this is the beginner way to write this in J. If you're disappointed that this is too readable and easy to understand, and you were hoping for something more exotic to impress your friends and terrify your enemies, then I have just the thing for you. This right here is a complete standalone J program that fills a 50 by 50 grid with the number 4, runs the sandpile simulation until it stops, and then outputs the results. And okay, if you want some color, you can borrow 2 RGB. Code Golf is a game programmers play where you try to express an idea in as few characters as possible. And actually, this is the shortest version of the sandpile simulation I could think of, but it's also pretty much the natural way to write it in J, at least for me. The only thing I really did to golf it was to remove all the extra spaces. If you have any interest at all in J, I encourage you to download J and try these lines of code for yourself, and then see if you can figure out how it works. If you're really brave, maybe you can come up with an even shorter way to write it. And again, I'll explain this entire thing character by character in the code review. But now, back to our program.
Sandpaint is the same as the modified grid pad I was showing earlier, but with a slightly bigger drawing area and some keyboard shortcuts for controlling the speed.
So now pressing space allows us to advance time one step with every key press. Then the rest of those lines just run the clock at various speeds, from once a second when you press 1, twice a second from 2, and so on. 4, 5, and here is 9, which is once a millisecond or as fast as it can go. And then 0 stops it completely. So that's almost it for Sandpaint. We are going to add a few more keyboard shortcuts in the next section when we look at the original Sandpile paper. So let's do some science.
There have been a number of papers talking about the mathematical properties of sandpiles, but it was actually a physics paper that introduced them to the world. It was called Self-Organized Criticality, an explanation of 1 over F noise. Now 1 over F noise, or pink noise, is the name of a phenomenon that crops up in all sorts of seemingly unrelated fields, from the level of rivers to heart rates to the fluctuations in electrical components. It happened to be first identified in vacuum tubes in 1925, but it was Benoit Mandelbrot who pointed out how widespread it was across the different areas of science. And his book, The Fractal Geometry of Nature, which was published 5 years before the Sandpile paper, seems to have helped popularize the concept. Now, the best explanation I could find for what makes 1 over F noise interesting actually comes from Mandelbrot by way of Martin Gardner. Let the tape of a sound be played faster or slower than normal. One expects the character of the sound to change considerably. A violin, for example, no longer sounds like a violin. There's a special class of sounds, however, that behave quite differently. If you play a recording of such a sound at a different speed, you only have to adjust the volume to make it sound exactly as before. Mandelbrot called such sounds scaling noises. Gardner goes on to give 3 examples of scaling noises. White noise, where the sound is completely random. Brown noise, where the pitch moves up or down by a set amount at each step. And then pink noise, which is somewhere in between. In particular, the spectral density plot of these noises, which is the bar chart you'd see on your stereo's graphical equalizer if you tried playing these things as sound waves, each has a very distinct look. And by the way, if you look at these exponents, you can see that in some sense, 1 over F noise is exactly halfway between white and brown noise. The mystery is, why would this random but self-similar scaling pattern crop up in so many different places in nature? What sort of physical mechanism could cause that? And that's where sandpiles come in. I'm not going to pretend to fully understand this paper. To be honest, even though it's short and I think I understand the basic concepts pretty well, some of the details were a little bit difficult for me, and I can't guarantee that everything I say here is completely accurate. But I'll do my best. The first part of the paper is an argument about connected systems in general. They give the example of how forces propagate through an array of pendula connected by springs. But the one-dimensional case isn't terribly interesting. The energy just moves down the line. I made a couple attempts to illustrate the point they were making with a 2D array of pendula, but I didn't really have the right set of dimensions to work with in a 2D physics program. And even when I replaced the pendula with balls on springs and turned off gravity, it's just really hard to tell what's going on in a physics simulation. Thankfully, the point the authors are making isn't tied to any particular system, and they introduce sandpiles as an abstract model that's easy to simulate. So let me attempt to make their point, at least as I understand it, using the sandpile simulation. So the first concept is a minimally stable state. Suppose you have the unit sandpile. You can't really tell, but this is now a 1x1 array with a single cell. We can put any value we like in here, but there are only these 4 values that make it stable. Of course, all the other unstable values in our palette are multiples of 4, so if we put any of those in here, it's just going to quickly wind down to 0. But if we put a number like 87 in there, then instead of 0, it's going to settle down to 3. 3 is the minimally stable state for a sandpile, in the sense that you can be more stable, but you can't be less stable without actually toppling. When we look at the system as a whole, especially a real system out in nature, we'd be very surprised to find all the units in a minimally stable state. Why? Well, the slightest disturbance at the edge sends a cascade of changes through the system, and every single cell gets affected. And since nature is messy and complicated, we'd expect lots of small disturbances to happen. So a uniform minimum stable state probably wouldn't last very long.
But as we encounter more and more disturbances, these little areas of more stable states start to build up, and they stop the noise from propagating. But every once in a while, a signal still gets through to one of the big areas. And that's the key idea.
As they write in the paper,
the system will become stable precisely at the point when the network of minimally stable states has been broken down to the level where the noise signal cannot be communicated through infinite distances. At this point, there will be no length scale in the problem, so that one might expect the formation of a scale invariant structure of minimally stable states. In other words, since nothing we've discussed depends on the size of the system, there's no particular constraint on how big your connected island of threes is going to be. So it shouldn't be a surprise that we get patches of all different sizes. On the other hand, and this is just my interpretation, maybe the bigger patches near the outside are more likely to get hit by these waves, and therefore they're more likely to get broken down themselves, whereas big islands towards the center would be more protected. And so maybe something like this is what leads to the 1 over f distribution of effects in nature. Of course, this argument is a lot less credible if it only works when everything starts in the minimally stable configuration, because then you have to explain why things start out that way. Now, if we started out with all 2s, it's already incredibly stable. You can nudge it all you want and it barely makes a dent. And if we start with a stable configuration at random, it's also likely to remain stable. In a purely random configuration, there's no particular incentive for these large patches of 3s to form. The trick is to start with an unstable system. For example, here's a 63 by 63 grid of 4s. And by the way, this is going to start strobing a little bit, so if you're sensitive to flashing lights, you might want to look away for a moment. Okay, it's done. And you can see there's a bunch of different size of islands around the edge. So this is an example of what the authors call a critical state. It's stable, but large portions are only minimally stable. And the hypothesis put forth in the paper is that an interconnected system that starts out completely unstable will naturally wind down into one of these critical states, rather than one of the more stable configurations that we saw earlier. Hence the phrase self-organizing criticality. So the next step was to test this hypothesis, and they did that on the computer using the Sandpile simulation. Basically, they started with a big random grid of numbers slightly greater than 3. And this is going to take forever to animate. And it's not especially interesting. Let's just fast forward. So hopefully this is a sandpile in a critical state. But with everything so mixed up, it's not really obvious how to tell. It does look different from the random piles we saw before. I can press C to copy this for a second, and then press R to see a random stable grid. And then X swaps back and forth. Notice that in the stable grid, we have lots of areas of black. And in this one, almost every black pixel is completely isolated. There also seem to be less 2s and 3s overall. In fact, we can look at this numerically. So plot. These red bars show the distribution on the completely random stable sandpile, and the blue bars show the distribution on the critical sandpile. The labels are off by 1, but these are 0, 1, 2, and 3. And I happen to record the counts when we started with all 4s, so here's that for comparison. So maybe there's something worth exploring in measurements like these, but getting back to the paper, the actual experiment was something like this. Generate a big unstable grid, let it settle, take a snapshot so we know the original state, then set any one of the cells to a 4, and let it play out. Finally, we're going to compare the before and after images and record the size of the change. If we toggle back and forth a few times, we can see the difference between the before and after pictures. And this image is just showing a 1 for every pixel that changed. If we want to count the size, we can just count the number of 1s in there or add them all up. So we can just test the copy versus the image, which gives us this giant array of 0s and 1s. And then we just add it together along both axes. So 859 things changed. Then they did this a bunch of times and averaged the result. They're actually a little unclear on the details here. Did they keep hitting the same spot every time and observe a progression? Or did they pick different spots? And if it was different spots, did they reset the array each time? Or did they keep the cumulative effects? Also notice there's a bunch of dark areas inside the perimeter where cells might have been affected during the run, but then settled back to their original values. Now they did include a graphic which shows an image like this filled in, and that makes me think that anything that got touched anywhere during the effect counts, meaning the size of this change actually should have been bigger than 859. So anyway, given those minor uncertainties, let's try and reproduce their experiment as best we can and see what happens. Of course, obviously, rather than doing this over and over again by hand, we're going to let J do the work. All right, so here we are in the J terminal. We'll go into the sandpaper locale, and here's our golf sandpile verb. This generates a random unstable sand pile and lets it settle down. They used a 50 by 50 array in the paper, so we'll do the same. Now we want to run the simulation after setting a random cell to 4, but also capture every frame of the animation. That way we can see exactly how it differs from the original on each frame. Once we have this, we can insert the logical OR operator between all those frames and see every cell that was touched. So let's cram all that together into one verb. And then this next one lets us run as many experiments as we like on that one initial configuration. The pound sign is making copies, so I'm acting as if we reset the simulation before each change, rather than saving the changes at each step. And that's pretty much it. The next few lines are just functions we'll need to make a logarithmic plot of the affected area sizes. So we'll let it run for a minute and collect the results. This actually takes quite a few seconds to run. So this ran 50 trials, 200 runs each, and then for each trial, created a histogram with the results broken down into 99 different bins, representing the log scale between 0 and 2,500, which is 50 by 50 and thus the maximum possible size of the reaction. Now we can take the average of those and let's plot it. This is just setting up the way the plot's going to look. And it gave me an error. So I need to make a slight adjustment to my logarithm function. Yep, that worked. And their claim is that the distribution of this function should approximate the function f of x equals x to the negative 0.98. Here's a plot of our data versus that function. And if we move it down a little bit, it seems to fit. So here's their results. Note that their graph only goes up to 1000. They say that this fall off to the right keeps smoothing out as you make arrays bigger and bigger. Even looking only at the middle, I don't really understand what they did to get a graph that smooth and close to the line, but maybe they're just better at plotting. Certainly my own plotting skills need some work, especially in J, but it does look like the general idea checks out. So just based on this experiment, not only do unstable sand piles settle down into critical states that give rise to lots of different reaction sizes, but those sizes tend to follow something close to a 1 over f distribution. By the way, the bottom chart in the paper came from running the same kind of simulation in 3 dimensions. Presumably they use cubes and distribute changes to 6 neighbors instead of 4. Maybe someone out there can make a 3D version of this software, and if so, I'd love to see it. Also, the charts on the right plot the distribution of reaction lengths, as in the number of steps the reaction took before settling down. So they do address a 1 over f distribution in the time dimension, although it's still not clear to me how any of this maps to a 1 over f noise in a frequency spectrum. Anyway, that's my take on the sandpaper. Like I said before, it was kind of a stretch for me to get my head around all that, so if I got anything wrong or just wasn't clear, then by all means, please set me straight in the comments. Meanwhile, let's shift gears from science to math and take a look at Sandpile Edition. Okay, so here's a new window with slots for 4 sandpiles. The animation here is just like before, except we're going to limit the palette to our 4 stable values, and on every tick, we're going to add the first 3 sandpiles together, let it settle, and then show the result on the right. We can draw in each of the first 3 sandpiles just like before. And then right-clicking one of the inputs causes it to copy the sum over, which of course creates a new sum. And then middle-clicking resets the input to whatever it was initially. So let's make sure this works. For example, 1 plus 0 is 1. Copy it over. 1 plus 1 is 2. Copy. 1 plus 2 is 3. 1 plus 3 is 4. And of course the 4 topples over. One more time. And that's how the plus sign was invented. Once again, I'll explain all of this in the code review, but I do want to point out these last couple lines. The middle click handler on SP0, that's this left one, sets it to an array of all 0. Then SP1 is an array of all 3s, our minimally stable sandpile. And then SP2 is set to ZSP, which is also an array of all 0s. The reason I made a variable for this one is that it's just a placeholder. It turns out that when you're adding sandpiles together, there's actually 2 kinds of 0. Let's take a look. I'm going to show you an algorithm for finding the other 0. You start with an array of 4s in the shape you want. So here it is, a 5 by 5 array of 4s. And you're going to step through until it settles. We can ignore all the sand that fell off. Now, we're going to subtract each of these values from 4. The 0s become 4. If we had any 1s, we would turn those into 3s, but we don't. The 2s stay exactly the same, so it's just the 3s left, and they become 1s. Because, of course, 4 minus 3 is 1. We settle this one more time, and whatever's left is our 0. Now, before we try this out, let's set our expectations. There's no way we could ever start from this pattern, add sand to it, and get back to that simple plus sign or even this array of all zeros. We can set any particular square to 0 by adding to it until it topples, but every time you send a grain of sand off the edge, you're also sending at least 2 grains back inward. You can never clear out the board. In fact, if you think back to the sand piles that we saw in the critical state, remember we noticed that all the zeros were isolated? That evidence seems to suggest that it's just plain impossible to get 2 empty squares next to each other unless you had those empty squares to begin with. It seems like it ought to be possible to prove that statement, and there's a bunch of math papers out there about sandpile, so maybe it's already been done, but for now let's just call it a conjecture. Point is, there's nothing we're ever going to add to this magic 0 that's going to give us back a completely empty sandpile. So this new 0 only works for some of the sandpiles. So let's see what happens when we add it to our minimally stable configuration. I'm going to just go ahead and draw it by hand. We've got a plus in the middle, empty square there, checkerboard pattern towards the edges. And there we go. All zeros plus all threes plus the magic 0 is all threes. Okay, so before we get too carried away, here's a restatement of the algorithm to construct this thing in J. Now, I can draw whatever I want in this third area, and when I middle click, I get the 0 sandpile back. If we set the other 2 sandpiles to all 0, it's obvious that adding these 3 together should give us the ZSP. But also, if we add 3 copies of ZSP together, we get ZSP. And by the way, that's not a commonly accepted name or anything, it's just what I called the variable. Now, I actually first learned about sandpiles from a really great Numberphile video, which I've linked in the description, and in which Dr. Luis David Garcia-Puente does a pretty deep dive into the math of these zeros. According to him, the set of sandpiles for which this 0 works is precisely the set you get by adding something to the array of all threes. That's why I put all threes in the middle. So it turns out that if you take the set of sandpiles you get from adding anything to the sandpile of all threes, then that forms a group under sandpile addition. I don't know if it has a special name or anything, but given the original paper, I think of it as the critical group. Now, when I say group, I mean group in the mathematical sense, which just means that it follows these rules. The sum of 2 elements of the group is an element of the group. It doesn't matter how you parenthesize a series of operations. There's some identity element that you can add to any element in the set and get back that original element. So that's ZSP in our case. And for every element, there's an inverse element you can add to it that gives you back the identity. As it happens, it's also an abelian group, which means that A plus B is the same as B plus A. By the way, this particular slide is basically a docstring, but it is actual J syntax. If we collected all the critical sandpiles into a rank 3 array called G, and if we had a definition for this inverse function, then we could turn all this into a verb and actually run it as a test case to prove that for every single triple ABC of elements, these rules actually apply. In fact, generating G isn't all that hard. You just have to list out numbers in base 4. Of course, the problem is that you need 25 digits, and 4 to the 25th power is a gigantic number. So even if you packed the sandpiles down to 7 bytes each, it would take like 8 petabytes to store them all. But just as an example, this line right here generates every possible 2x2 sandpile. And again, it's just counting to 4 to the 4th power in base 4, and then arranging them nicely. So other than being completely impractical for the larger case, it's not hard to generate the sample. But what about this inverse function? Well, I was going to say that I had no idea how to do that, but then I just tried it. And because I'm a super genius, pretty much the first algorithm I thought of worked. Haha, look at that. This plus all threes equals, wait, oh man. All right, so it doesn't actually work. This is showing all zeros, and we know that this should add up to all threes. It's just a display bug. We have negative numbers in the grid, and that's not supposed to happen, so the coloring function doesn't account for it. So it seemed like this was kind of a dumb idea. But it turns out that if we keep just adding the 0 sandpile until these holes fill up, here's adding 0, 0, add 0, and now it stops changing. If we keep adding the 0 sandpile until all those holes fill up, this approach actually does work. Again, I don't have a formal proof of that statement, but as far as I can tell, it works. And no matter what I draw here, I can press I and get the inverse. So it turns out that's an easy problem to solve. However, even though it's easy to generate the inverse with the program, it's not so easy to guess what it's going to look like, even if you know the algorithm. And that's why I said back at the very beginning of this video that this calculator doubles as a puzzle game. For example, we just saw the inverse for all threes, but could you draw it from memory? I can't, but it's kind of fun to just try and figure it out. So Okay, so there's my answer. This answer isn't actually part of the critical group, but who cares? Let's solve the puzzle. We can keep adding a to it, and that's the real answer. So yes, if someone wants to take this idea and turn it into a real game, I'd love to see it. It's kind of fun to just try and solve this. If you press P, you get a random sandpile in the middle here. The random ones you get aren't nice and symmetric, which I think makes them quite a bit harder. Give it a shot yourself and let me know how you do. Meanwhile, that's pretty much all I have to say about sandpiles. But I will leave you with what may be the most profound and important equation in all of sandpile mathematics. All threes plus all threes plus all threes. And that, boys and girls, is where plus signs really come from. Hey, thank you so much for watching my video. If you enjoyed this and you want me to make more of these, I would really appreciate it if you shared the link with a friend. And just a reminder, if you want to know what all those squiggly marks are about, subscribe to this channel and click the little bell icon to get notified when the code review comes out. If you don't want to wait, all of the code is already up on GitHub and there's a link to it down in the description. There's also a link to the Sandpile paper and a bunch of other things related to Sandpiles that you might want to check out. And finally, if you watched all this and you're not a programmer, or you are a programmer and have no interest whatsoever in learning J, then I'd really like to hear what you thought of this video. In particular, the style where you're seeing all this code but not necessarily expected to understand it. The next video I'm planning is on the Mandelbrot set, and whether I split it into a general presentation followed by a code review, or just do it all together, is probably going to depend on the response I get to this one. So please share your thoughts in the comments. Also, let me know what I can do to improve. Feel free to ask questions, or if you make something related to all this, send me a link. I'd really love to hear from you. Anyway, thanks for watching, and I hope to see you again.